Hey everyone, welcome to the first video for section 3.6, talking about the method of variation of parameters. So this is another method for solving non-homogeneous systems. As you'll see, it's a lot more complicated, but the main benefit it has is that it always works and gives us our theoretical results for solving non-homogeneous equations. So it tells us that we can always find a solution, and it gives us a way to find the solution, even if we may not be able to solve it explicitly every time. So it's going to be a little bit of a longer video going through the whole method, but let's just go ahead and get started with it. So we're talking about here is the variation of parameters method. And the idea for this is, well, sometimes undetermined coefficients doesn't work, mainly because sometimes maybe you can't guess what this y of t is going to be from the g of t on the right-hand side. And the main way this wouldn't work is, well, maybe whatever function g is, if you take derivatives of it, you don't get the same functions back, you get different types of functions, right? The main way we were able to guess the y of t before was because we had a sine function. You differentiate sines, you get cosines, cosines go back to sines, so you only have to guess those two things, and I should be able to figure it out. If the function g is a lot different, so say g of t is something like tangent of t, or g of t is t to the minus 2 e to the t minus 2. If it's positive 2, we can guess the right thing, but t to the minus g of t, when you take derivatives of that, you just get lower and lower powers of t, and they don't ever stop. So it's not really, you can't really guess a solution from there and then try to find the coefficients because you'll get infinitely many equations to solve for, which is not really something that you want to do. So if this fails, we need some other method to try to solve this equation, and that method is the variation of parameters method. So points about this method. So the first one, which is the important, is it's a general method. It works for any function g of t. It doesn't matter what the right answer looks like, you can always use this method. So this is a general method in the sense that it always works. I'm going to put works in quotation marks there because I mean works in the sense of like it theoretically gives you a solution, not that it always works, then you can always solve the problem. As we'll see when we do the example and write out the formula, we'll see where we could have issues and try to actually solve it out by hand. And the second point of us is that it does end up being more complicated than undetermined coefficients. And this should kind of be expected because if we're going to get a method that works in more situations, it's probably going to have to be more complicated just because if it's going to solve more problems, it's going to have to have a little more flexibility in it to be able to solve those problems. So it's going to be more complicated. It's going to be pretty much a strict method you can follow, but it does work for any right-hand side you want. Whether or not you can do it explicitly is sort of depends on what the functions are, but you will get a solution this way no matter what. All right, so let's go ahead and start thinking about this method. So we're trying to solve y double prime plus p of t y prime plus q of t y equals g of t. And here we're going back to the general, not necessarily constant coefficient case because we can solve it in this case just as easily as we could with the other case. Again, working these out by hand, it's going to be a lot easier to do this by hand if you have constant coefficients, which is probably what you'll see on exams and stuff. But it works in the general case as well, so we'll do it all in the general case. What do we already know about this type of problem? Well, we know there are functions y1 and y2, so that any solution to y double prime plus p of t y prime plus q of t y equals 0 is of the form c1y1 plus c2y2 for c1 and c2 constants. Right, this was our theory from section 3.2 where we talked about what do the forms of solutions to homogeneous equations look like. We know they're always of this form, and these y1 and y2 make a fundamental set of solutions. In particular, this means that the Wronskian of y1 and y2 is not 0. That'll come up a little bit later in this video. So we know if we take these solutions and add them together with constants in front of them, we get solutions to the homogeneous equation. So what we're going to do is we're going to vary the parameters and they vary those constants and see if we can solve the non-homogeneous equation that way. So we will try to solve p of t y prime plus q of t y equals g of t, the non-homogeneous equation, by guessing y of t equals u1 of t times y1 of t plus u2 of t y2 of t. And the hope with doing this is that by including the fundamental set of solutions in my guess, something's going to cancel out, something's going to make it look a lot better because of having y1 and y2 in there. And the hope is that we'll be able to pick the functions y1, u1 of t and u2 of t to make this solve my non-homogeneous problem. Right, we're changing constants into functions, so now we are varying the parameters, hence why this is called the variation of parameters method. So if I want to then take this y and plug it into my equation, see if I get g of t, I need to take two derivatives of this y. So let's take the first derivative, and this just comes from the product rule. So y prime of t is what? I'm going to write these terms in a weird order, and I'll explain why when I'm done. u1 of t, y1 prime of t, plus u2 of t, y2 prime of t. That's the derivatives hit the y terms, plus u1 prime of t, y1 of t, plus u2 prime of t, y2 of t, y2 of t. All right, so I have the product rule terms. All four terms are there. Now, what we're going to assume, and we'll sort of see how this helps us out at the end when we start writing things all together, we're going to have two unknown functions, u1 and u2. That means I'm allowed to have two conditions on my functions to try to be able to solve them out. So we're going to get one by plugging in the equation. Where do we get the second one from? We get that one from right here. And we're going to assume that this term here, we're going to assume this is 0. What this is going to do for us is, one, it's going to make it so when we take the second derivative, we have no second derivatives of u1 in our equation, because the second derivative of u1 would come from this term when we took another derivative. And secondly, you'll see at the end, it's going to bring the Wronskian back into the picture, which, since we know is non-zero, we can sort of solve things out using the Wronskian. So now let me take the second derivative of y, assuming that this last part is 0, so I just need to worry about the first two terms here. So I'm going to get four terms again for y double prime of t, and I get that for my second derivative. Just take the product rule again, that's what you get. So now what we want to do is we want to use our equation. So I want to take y double prime, y prime, and y, and shove them all into my original equation that's up at the top here, where I have this equal to g of t. And the goal is we're going to be able to use this to give a second condition on our u1 and u2. So let's go ahead and just plug that in and see what we get. So I'm going to get, well, I have y double prime plus p of t y prime plus q of t y equals y double prime plus p of t times y prime plus y. Now, we've seen the sort of shenanigans I'm going to pull next before. And what we want to do is we want to group terms based on which unknown function they have in front of them and how many derivatives of the function they have. So I want to group my u1s together, my u1 primes together, my u2s together, and my u2 primes together. Right, we did this the same idea we pulled with reduction of order and stuff before. So let's go ahead and group the terms along those lines. So just taking this expression here, this is the same as, so u1 prime only shows up in this first term, and then u2 prime also, u1 prime only shows up here, and u2 prime only shows up here. Oh, I forgot something. I forgot my q of t. Multiplying this guy. So u1 shows up there, u2 prime shows up there, and then I get a u1 of t times what? Well, I have a y1 double prime in the first term here. I get a p of t y1 prime from here, and a q of t y1 from here. So plus p of t y1 prime plus q of t y1. And similarly, I'll see I get a u2 of t times y2 double prime plus a p of t y2 prime plus a q of t y2. And I want this to equal g of t. Now what do I notice on the left-hand side? Well, this here is exactly the ODE I was trying to solve. Double prime plus p of t y prime plus q of t y, but y1 was the solution of the homogeneous equation. So this whole term goes to 0, and so does this whole term by the same logic. So what I'm left with, after all this is said and done, is u1 prime of t, y1 prime of t, plus u2 prime of t, y2 prime of t, equals g of t. And this is what my equation gives me. Now I want to take this and I want to add in my condition from before. So my condition from before was that u1 prime of t, y1 of t. This is the assumption we made partly through the proof, plus u2 prime of t, y2 of t equals 0. And so this is what I want to solve for u1 and u2 to get my coefficients to give me my non-homogeneous solution. Now, this is a linear system with two equations with two unknowns, and we can just think about it as doing this for each point, or we can just solve it out for each point, and we'll get a function of t out of that. So how can we solve this equation? We can solve the equation by elimination. And if you do that, what you will end up seeing is that your solution looks something like this. You'll get u1 prime of t equals negative y2 of t g of t over the Wronskian of y1 and y2 at t, and u2 prime of t equals y1 of t g of t over the Wronskian at t. And so you see, if you look at the equations, you'll see how you do it by elimination, right? You multiply the first equation by y2, the second equation by y2 prime, you subtract the two, you'll end up getting the Wronskian coming out of it, and you can just solve out for the constants based on that. The constant you divide by then is the Wronskian. So here is your solution to this, and this gives you equation solutions for u1 prime and u2 prime, and then to solve for u1 and u2, you just integrate these out. All right, that's all I have to do. You find the derivatives, you integrate, you find the actual functions. So that's the general method for variation of parameters. It looks complicated, it looks kind of nasty, and to be honest, sometimes it is kind of nasty. But in a general problem, all you'll be asked to solve it explicitly, and it looks a lot better when you have explicit functions you're putting in instead of these arbitrary variables that are just flying around everywhere. So the next video will have an example of solving a problem using the variation of parameters. So hopefully that will make things more clear if you look at that. All right, so that's the point for this video. The next one has the example in it. I'm going to give you a problem to work on with this video. All this is I want you to write down what you would want to plug in for capital Y to try to solve this problem of variation of parameters. This is all I want you to do for this problem, the next problem here that I'm going to give you for this video. So let me write that up for you right now. All right, so here's a question for you guys. I just want you to write down what you would start by plugging in for Y of t, capital Y, in order to solve this problem of variation of parameters. So if you need help with that, go back and look at the video. You should be able to figure out where I went with it from there and get the right answer for this. All right, thanks for watching, and I will see you in the next one where we do the example for solving a problem by variation of parameters.